Metallic bonding and properties, GCSE Chemistry, IGCSE Chemistry, and High School General Chemistry.
Chemistry Explained are chemistry lessons designed for you to participate in. So make sure that you are writing notes and completing tasks on paper or on tablet. Move through the lesson at the pace that suits you. Skip ahead or move back as you wish. Most importantly, when prompted, pause the lesson, complete the task, but taking your time and thinking the problem through. Resume and check and correct your answers before moving on.
The lesson overview will start with metallic properties, giant metallic structure, metallic bonding, explanations of properties and some uses, and then alloys, properties and uses. So let's review the properties of metals by comparing them to ionic substances and simple covalent molecular substance property. So here are a list of properties. Decide whether tick or cross they are shown by ionic, tick or cross they are shown by simple molecular, and tick or cross they're shown by metals. Come back to compare your answers with mine when you are ready. Of course, there will be exceptions to the general description of typical properties of metals, simple molecular and ionic. Keep to the typical rather than the exceptions. So here are the typical properties. Shiny appearance, limited to the metals. High melting point, ionic substances and metals have high melting points. Solubility in water, ionic substances dissolve in water. Simple molecular may or may not, but it's not a typical property. Metals do not in general. High density, that's typical of most metals. Malleability and ductility, the ability to be bent or to change shape, a property exclusively of metals. Conduction as a solid, ionic, no. Simple molecular, no. Metallic, yes. Conduction as a molten liquid, ionic, yes. Simple molecular, no. Metallic, yes. So the conduction is a key property. Metals conduct as solids. Ionic substances, in contrast, only conduct as liquids, or you will recall, in solution. So we're going to take metallic structure and metallic bonding together. So metals form a giant lattice, by which we mean there are large numbers of atoms arranged in a regular way. And we would normally represent them in diagrams such as this, where we have layers of atoms lying on top of each other. However, this is just a small portion of the giant lattice. It extends to the right, to the left, above and below, and in front and behind. So this is a two-dimensional picture of a small portion of a giant three-dimensional lattice. The atoms or particles are close and may be called an array. So we have a close array of atoms. And an atom, of course, has a nucleus, which is positive, and I've drawn a negative sign for the outer shell electron. So in this particular example, we have a positive nucleus and a negative electron in the outer shell. Of course, there may be in other metals more than one outer shell electron. Now, the outer shell electrons are lost. So the metal atom becomes a positive metal ion by losing its outer shell electron. So each of the atoms here, nucleus and outer shell electron, becomes a positive ion with an electron that is no longer located in the atom, but doesn't have a location, it's delocalized. So we say that these electrons, which were in the outer shell of each atom, but which have been lost from those atoms, are delocalized, and it may be referred to as a sea. So a delocalized sea of electrons. And of course, we have a giant lattice of positive ions. The atoms have become a positive ion and a delocalized electron. The delocalized electrons can move throughout the structure. They do not have a position. The positive ions are held in place and form a giant lattice. We would account for metallic bonding as the electrostatic attractions between the positive metal ions that are formed by the loss of their outer shell electrons and the delocalized electrons that result. So we've got a sea of delocalized electrons and a lattice of positive ions, otherwise known as cations. That may or may not be in your specification. So the positive ions are attracted to the delocalized electrons, and those attractions hold the ions in place. Those electrostatic attractions are strong, and therefore metallic bonding is strong. We now need to explain the properties of metals that we reviewed earlier on in terms of the theories of structure and bonding, and also consider some of the uses of metals. So, typically, metals have high melting and boiling points. Here is our idea of the lattice of positive ions surrounded by delocalized electrons. Could you suggest a reason as to why these ideas will produce high melting and boiling points for metals? Pause, write something down, come back to correct when you are ready. Okay, so we're explaining the high melting and boiling points because the metallic bonding between, which is the attractions between the positive ions and the delocalized electrons, is strong. And it's between all the particles in the giant lattice. So all of the positive ions are attracted strongly to delocalized electrons. So therefore, a lot of energy is needed to break those attractions, those bonds, and therefore we have high melting and boiling points. Another property we discussed was ductility and malleability. The explanation for the ability to change shape or to be pulled into a wire is based around the fluid nature of metallic bonding. Could you formulate a sentence or statement which explains clearly why metals can change shape or be pulled into wires? Pause, come back to correct or check your answer when you are ready. Okay, so my explanation is that the fluid nature of metallic bonding allows the layers of ions to slide over each other easily. So my little schematic here The layers slide over each other. We haven't had to break any metallic bonding. We've just adjusted the bonding. The bonding is fluid. The electrons, the delocalized electrons, can change position to adjust. So there are no energy barriers to sliding layers of ions over each other. Metals conduct electricity as solids. Can you write a statement that explains why that is so? Pause, come back to check when you are ready. Okay, so to reveal, my argument, the standard argument, is that the delocalized electrons, which are charge carriers, they are negatively charged, are able to move throughout the structure, and that occurs without disrupting metallic bonding. Delocalized electrons, by their nature, are free to move. So therefore, a movement in one direction or another, carrying charge of the delocalized electrons, is perceived or detected as an electrical current. But metals are also good conductors of heat, which we call thermal conduction. The mobile electrons again transfer the energy through the structure. So let's look at the use of copper. Copper, for your information, has high conductance and ductility. Can you think of a use that copper is put to in everyday life that relies or depends on the high conductance and ductility of copper? Pause, have a think, come back when you are ready. Okay, it's used in electrical wiring. You may or may not know that. So unpeel an electrical wire, you will see the distinctive color of copper. Very high conductance, easily pulled into wires. It's the metal of choice for everyday electrical wiring. And finally, let's consider alloys, the properties of alloys, and some uses. Let's start our discussion of metal alloys by thinking about pure metals, which tend to be soft and malleable. The layers of atoms are able to slide over each other very easily. That means pure metals have few practical uses. A good example is pure gold. You'd think, oh, wonderful, I'll have a pure gold wedding ring, 24 karat. It's too soft and will change shape very markedly. So I would recommend 12 karat or a maximum of 18 karat. To make metals more practical, more usable, metal alloys are made, which are mixtures of metals. The presence of different sized metal atoms disrupts the regularity of the layers that one sees in pure metals. So rather than having nicely arranged regular layers of the same size of atoms, if we put in some different size atoms, you can see that the regularity of the layers is disrupted. That is because we've got different sized metal atoms inserted. Now that may also include carbon. Because of that, the alloys are much harder than pure metals. Pause. Can you come up with a reason for why alloys are much harder than pure metals? Come back when you've had a think and written something down. Okay, So the answer lies in the ability of the layers to slide past each other. The fact that the regular layer structure is disrupted means that the layers can no longer slide past each other as easily, and therefore alloys are much harder than pure metals. Let's think about some useful alloys. The most used alloy is definitely an alloy of iron, steel, or steels. There are lots of different types of steel. Very useful to make machine parts and simple tools like hammers. Different steels are made by adding different amounts of carbon. So you can get harder and softer steels by varying the amount of carbon that's added. But of course, compared to the pure metal, all the alloys are much harder and therefore much more useful. You'll see here in the hammer, there's probably more than one type of steel used. It seems that this handle section is probably a stainless steel that is a corrosion resistant, and that's achieved by adding other metals such as nickel, chromium. A further alloy you should be aware of is brass, a mixture of copper and zinc, around about 60% to 40%, something 65 to 35, something like that. And it's another useful everyday alloy that you will meet. So you now need to practice. I suggest you first of all do the textbook end of chapter questions, for which you probably can find answers, and then move on to past paper questions from the particular exam board that you are taking. If you don't have immediate access to those, there's a website, Maths and Physics Tutor, which has collections of past papers and answers by exam board.